Hello, everybody, and welcome to Bitshala's first Bitdev seminar. And here we are going to talk about Musig2 with Saravanan Mani. And he is an engineer at Bitgo. Bitgo has recently integrated Musig2 into their co-custody model using Taproot. So that's pretty exciting. And we are going to deep dive today about the maths behind Musig2, the reason, the mechanism, and how all this magic works. So I'm your host, and Saravanan will be guiding the discussion. So in the meantime, feel free to raise your hand for asking question, or put them in the chat box. And as the discussion is going on, we will get towards those questions. And also feel free to interrupt any of us at any time if you have any suggestion, comments, or anything. So let's get started with it. Saravanan, the stage is yours.
Thank you, Raj, and thanks everyone for joining. So, about this discussion, just one heads up. This is going to be a lot of math, but very simple algebra math. But since it's going to be a lot of math, it's better to stop me whenever I'm not making any sense in any stage and get clarity. Then we can move forward. That would be a better strategy to for this presentation.
Totally.
Yeah. Okay. I'm going to start it. So this presentation is primarily about basics about Taproot and music, just to get the intuition behind why Taproot and why music and how it works, how it is designed in this way. That is a primary goal. So few warnings and disclaimers. It is going to be math, as I said, but it is going to be simple and very repetitive. So no hard challenges. And then the math and the Bitcoin scripts and the diagrams that we use are slightly modified to make it more easy to understand. So it will not be completely strictly syntax will be right one. So it will be slightly modified. So that's the basic thing. Now we'll start. So before Taproot, what is the problem that Taproot is trying to solve? The problem that exists before the Taproot. That's the first thing that we are going to discuss. So here you can see as an example, we have P2SH, P2WSH, or wrapped P2WSH. These are the multi-sig scripts that we have within the Bitcoin. So as an example, within P2SH, a redeem script will look like it. In case of Bitgo, we are going to look Bitgo as an example scripts in this whole presentation. So Bitgo is a 2 of 3 multisig, user key, backup key, and Bitgo key. So primarily user and Bitgo key are happy path keys, kind of the happy path keys. In the rare scenarios, the other two combinations are used. So how the scripts will look like is this. And starting from here, this is the script, very basic one, 2 out of either user, Bitgo, backup, of 3, the check multisig output. That's it. If we present user signature and Bitgo signature along with this redeem script, then it will be a valid one. So that is a basic fundamental redeem scripts that we use in the Bitgo wallets. The problems, obviously, one is the weak privacy. Because we are exposing all 3 public keys over here, and block space is a little bit higher because we require to present 2 signatures and 3 public keys and the rest of the opcodes. So is there a way to optimize this? Is there a way to improve this privacy? Is there a way to reduce this block space consumption? So inherently the fee cost that is involved with the block space. So those are the 2 problems that kind of Taproot is trying to reduce here, along with other major problems. So to understand, to proceed further, we can get an idea, get an intuition from the scripts. What do we mean by that? So every script can be rephrased in a way like OR conditions. Example, in this scenario, what 2 of 3 is nothing but either user Bitgo or user backup or Bitgo backup. Even if it involves much complex scripts, we can rephrase something like this. Let's say for a Lightning Network channel, where there will be some time blocks will be involved there. You can rephrase that as a OR conditions. You can rephrase that as OR conditions, right? So that is one of the advantage that we can see if you interpret it in the right way. So in this example, what we can do with this rephrasing is, if I want to present user signature and Bitgo signature, I don't need to talk about these two combinations. I can simply have a hash of this one, and take a hash of this one, and only present signature for this user and Bitgo. Then the verifier can simply take hash of this one and combine with these two hashes, and it checks that the output script matches with this hash. We can hide the other conditions from these OR phrases without compromising the verification. You get the basic idea, right? If any of you is not clear about this, you can ask any questions around here. This is one of the very basics about the Taproot.
Right. Yeah. So in Taproot, like all the possible OR paths are basically put inside a leaf. So we'll talk about it. We'll talk about in the next slide, I guess. And then only the path that we are interested in gets revealed, and all the other paths, we just only need the hash in order to prove that those are part of the whole tap tree, instead of like revealing what exactly those paths, like those other paths are.
Exactly. So with this understanding, how Taproot uses this advantage. So Taproot has two different kind of spending approaches. One is called keypath spending, another one is called script path spending. Let's not talk about the keypath spending for now. Let's just ignore that. Let's just assume that Taproot doesn't have a keypath spending at all. This is what whole Taproot is. So whatever that just Raj was explaining, every leaf will contain the combinations, the conditions that can be made successful. So the same user Bitgo, user backup, and Bitgo backup. All of them are just a scripts, and we can take a hash of it, hash of this, hash of this. Then if we have two different hashes, we can combine these two hashes, and finally everything will end up with the final root hashes. Another kind of metallized tree approach. That's what we are looking at here. Nothing special. So in this way, whatever we just discussed, here we are doing that as a tree approach. So if I want to present script signatures for user and Bitgo, I just have to present this hash BC. Okay, just 32 bytes, let's say for 32 bytes. That's it. Because this 32 bytes represents this script, and this scripts as a OR condition here, and that's what this 32 byte is representing here. So the verifier can simply verify the scripts with the, let's assume we have a user signature here and Bitgo signature. The script is valid. Now he can just take this part and take hash of it and just hash these two and hash this. If this matches the output script that we are spending, then we ensure that we are spending a right script successfully without compromising anything. You get the idea, right?
Right. Yeah.
Okay.
So the whole tree is verified just by the hash BC.
Yes.
Can I have a question?
Yes. Yes. Go ahead.
Yeah, please go ahead.
Yeah. So, I mean, I understand this thing, but how do we do the communication? How do we collect the different hashes? Is there any set protocol that people normally use, or is it through partially signed Bitcoin transaction or something like that?
The voice is not. Sorry, the voice is not very clear to me, Raj. If you are
So
very
like
clear.
his question was like, how do we communicate these hashes? So for example, like how does we communicate hash BC? So
Communicate to other signers.
yeah, basically like it goes inside the witness script of Taproot transaction, right?
Yes, yes,
So
yes,
while
yes.
while constructing the witness of the transaction, you will include the user Bitgo check multisig, that leaf, the whole leaf, then hash BC, and that's it. And then there are some control blocks and stuffs like that. So all these informations are there in BIP 341, if I'm not wrong. That's the Taproot BIP. And so it's basically inside the Taproot protocol how you communicate these hashes together.
In short, the transaction witness will contain this information. So let's assume that we are going to spend this Bitgo backup combination. That is the one that we are going to spend. In that case, the witness will contain this script and this hash and this hash. That's it. So using this information, this is called control block. Yeah, control block. The path information will be here. The exact path information will be here. Using this information, they can reconstruct this hash ABC.
Right.
So the communication, I think details are outlined in bits, right?
Yeah, the communication of these things are detailed in BIP. It's basically the same as like putting the required value inside the transaction witness. And Taproot specifies a certain ways of specific like protocol and specific structure in which you have to provide these hashes. You just have to follow that structure.
Thank you for that.
Okay.
Any other questions around here? Okay. So we just discussed about this script path approach, how it is a little bit of optimization because currently only the privacy is improved here, right? Because if we are going to spend this hash A script, we don't need to reveal these two scripts. So user will not, the verifier will not see a big backup key exist and what is the other two combinations as well. So it's completely hide from the verifiers. So they will only see this hash BC. That's it. So that is a privacy improvement. And since it is a very simple 2 of 3 multisig, let's assume this is a very complex multi-layer tree. In that case, the block space is also improved because the logarithmic nature of the trees will help to reduce the size. What do I mean by this? As I said, if we are going to spend this path, we don't need to give this information, right? Only this hash and this hash will help us because these two will be combined here, and these two will be combined here, and it will be the output. So if it is a very complex tree, the logarithmic nature of this tree will help to reduce the block space for a complex script. That is one another advantage that we discussed.
Right. So there can be like n number of like possible spending paths, and
Yeah.
you only need to specify log n of multiplied by 32 bytes of it, and along with the script spending path that you are interested in. Otherwise, like if you imagine a P2SH or P2WSH, the whole spending condition you need to reveal inside the witness, and that can be like really big for if you have multi-path spending conditions, very complex and something like that.
Let's say some 2 of 50 multisig. In that case, this will be much more efficient than
Right.
this one.
Yeah.
So far we discussed about the script path, how it is help us to reduce the block space, so fees, and increases the privacy. Excuse me. So now we are going to make further improvement on top of it. Taproot does this using this script path approach, key path approach I initially mentioned. Now, what do I mean by this key path approach? So let's assume magically there is a way to, instead of doing this, we can simply add user and the Bitgo key. Just add it, both 32 byte and 32 bytes plus 32 byte, both add it and arrive at a single 32 byte public key, an aggregated public key. And the signature will also like aggregated signature, let's say 72 byte signature as an example, hypothetical example. A single signature and a single public key both are aggregated. Two signatures are aggregated into one signature, and two public keys are aggregated into one public key. If we can magically do that, then we can do one thing. Whatever the happy path, I mean the very commonly spent condition for the script that we are trying to spend here. In case of Bitgo, the user key and Bitgo key is the very commonly spent 99% of the time. User key and backup key are the one that being spent. These two are very rarely. So let's keep this in a key path, and the other two combinations just are restructured and kept it as like this, the same script path spending approach. It is not a big deal. I mean, it's almost the same one. So but it requires a big if, right? We have to magically add this public keys and add this signatures and verify this added aggregated signature. So how we can do that? That is the question. Is there a way to do that?
So here we are talking about the key path spending, right? So in the key path spending, so that is like another leaf which only allowed to contain one signature and one public key. No script inside that is allowed to go, right?
Yes.
So here the question is like, we wanted to do an happy path, but our happy path is like a multi-sig situation where user and Bitgo's keys are involved. So how do we transform that into a single key spend?
Okay. So that is a basic question.
Right.
There are a few more points to be discussed here, but we'll come to that later. So if anyone has any questions around it, just go ahead, or we can continue with the next slide. I'm hearing some.
So like Einstein is saying like what's the happy path means. So happy path means like the situation that is going to occur most of the time. So in Taproot there is a thing called key path spending. In key path spending, your data consumption inside the witness is the lowest. So the most viable situation, the most viable spending condition that is going to happen most of the time, you want to include that inside the key path spending, because that will result into the lowest amount of lowest size of the witness for most of the cases. So that's what happy path means. Happy path means like everything is good, it's like business as usual, nothing goes wrong, and you are using the most used spending condition that was supposed to use. In case of like this multi-signature, it's user and Bitgo signing together and everybody is happy.
So I have a question continuing that. Like, is the happy path for pay to Taproot the same as like P2PK, like the fees, or is Taproot little bit more?
No, it's a bit more, because in P2PKH, the happy path will like public key and the signature and then the hash and check it. But in Taproot, you will also have to include the scripts path root, like the hash of the script path. So that's 32-bit more. And so here you will have like the public key, signature, check multi-sig, plus a 32-byte extra data. So it's a bit more than the P2PKH condition.
Okay, I got it. Thanks.
Okay.
So
Actually, on chain, only this public key will be exposed, this tweaked output key, and a signature to verify this public key is going to be the one. We will see how it will work. This will be completely hidden from the picture if we are spending this condition. This will not be even shown to the verifiers on chain. That is one of the biggest advantage. We will see how it will work.
right.
So it will be significantly, I mean, a little bit, because the signature is going to be 64 byte. The key, probably the key is going to be 32 or 33 byte. That's a setup here.
So
34 byte actually.
another
Yeah.
question was in the comment, Setu was asking, P2SH can just use script path. Can you elaborate the question? I didn't get it. Like, what did you mean?
So you are spending key path spending. You are talking about right now about key path spending condition, right? So can this also be there in P2SH, or in case of P2SH, we don't have to worry about key path spending
So
condition?
like in any other kind of SH, like apart from Taproot, there is no concept of key path or script path spending. Everything is like one single spending, right? So the reason we have like separation in Taproot is like we want to use the happy path, which is the most simplest spend most of the time, because that's smaller, and we want to like hide out all the complex thing that will come in case of something goes wrong. In P2SH, you can like translate this whole scripting policy, the whole tree, into a P2SH, but then you have to like reveal the entire script with its op-if, op-else, all the spending policies together inside the P2SH. So there is no obfuscation going on over there. So P2SH is like bulk dump the whole script into the witness and then like go through the execution. Depending on the input of the if clauses, certain path will be executed and certain path will not be executed, but those paths will also be dumped on inside the witness. You have to reveal everything.
Got it.
Yeah.
Sorry, one question for you actually.
Yeah.
I'm more on the composition side, how to make this the whole thing the output script. It's up to us how to make this happy path, or is it the wallet that makes the decision that?
Generally, like it's the wallet that will tell you, like the wallet will, like a wallet is basically a software that conforms to a specific spending policy. So the wallet, probably most of the time, the wallet will be only able to work with a specific structured tree that is predefined by the wallet software, right? For in case of Bitgo, this is the tree what it looks like inside the wallet. So you cannot go ahead and define the tree yourself, but there are other tricks called mini scripts and descriptor wallets, using which you can like define your own trees and stuff. So those also possible, but I don't think any of the wallets in production out there allows you to do that.
Okay, thank you.
The receiver defines the structure of the tree. It's up to the receiver how he wants to receive the, I mean, what is the conditions that he wants to spend after he receives the Bitcoin to the address. So in case of Bitgo decided since Bitgo always spends from user and Bitgo signatures, it decided to keep the efficient key path to spend this user and Bitgo combination, and another rarely spent approaches into the script path approach. If another wallet decides to have totally different scripts, let's say that a CEO of the company only can spend the entire Bitcoin from the input. In that case, he doesn't even need to do this aggregation at all. Probably a CEO signature will be sufficient, one single signature, because from the on-chain perspective, it is always look like a single signature and a single sig. Everything will be hidden from the on-chain. We'll talk about that, how that will be done in the off-chain, but it entirely up to the wallet creators or the spenders that he wants to receive the Bitcoin in the first place.
Right.
Yes.
Okay.
Thank you.
Yeah. So now we are going to explore how this magical part can be created from for this solution, for this particular key path thing. So hereafter, for some time, we will only focus on this particular area. Then we'll talk about this area. We will not be covering any further about this area, because this is where the Musig2 comes into the picture. How this aggregation of the keys is done, how the signature aggregation is done, how the verification is done, and those are related to the music. And we will talk about these two elements. Then we'll be done with this. So let's move with this. So first, before moving into the music, we need to we are just going to refresh what is digital signatures in the first place, just to get a basics idea and refresh our memory. So the basic question is this. This is the question. The goal is this. Let's say that for a given private key of the given public key, using a commonly known message, the signer needs to prove that he has the private key of the public key that is given to everyone, shared with everyone. So the public key is shared with everyone. Everybody knows the public key. The message is also something shared with everyone. The signer needs to prove that he knows the private key of this public key. That is a goal, ultimate goal of any digital signatures system. If with this understanding, let's try to create a very dummy, naive, stupid digital signature scheme using simple mathematics. To do that, in a hypothetical world, let's assume we have a mathematical operators like multiplication and division, something like that, where the special condition exists in that hypothetical universe. Let's assume something like that. So in this universe, we have a multiplication of two numbers, but there is no possibility of doing the division of those two numbers. What do I mean by this? You can multiply D and G, but you cannot get the D by doing this P divided by G. There is no such math involved in this hypothetical world. That is the assumption that we are going to make. How does this assumption is implemented is completely a different story. That is where the ECC elliptic curve cryptography comes into the picture, but that's not scope of our discussion here. So as of now, just assume that we have a math equation where multiplication is possible, but the division is not possible. That is a basic intuition. If that is the case, we are going to have a common number called G. We call it as a generator number. It is a common number for everyone who are using the Bitcoin. It is going to be a constant. That's it. Only the P and D will be varying. So the D is the private key, P is the public key, which is derived using this private key. That is the initial system. How does it done? Simple. We just multiply D with this common number G. In an example, let's take 3 and 2 and E. E is nothing but the message that we are going to use to sign this whole message. So we are just doing sample very basic math here, just D into G, which is 6. And let's say, as we discussed, there is no division involved here. There's no division possibility here. That is an hypothetical state that we decided. So it is not possible to derive from 6 to 2 and 3. We cannot separate that. That is a basic idea here.
So it's the same thing as saying like you cannot derive the private key from the public key. So D is our private key, P is our public key, and we can calculate the public key if we know the private key, but we can't do the reverse.
Yes. So just multiplying it, the value is multiplying it. The 6 is the public key here, 2 is the private key here, and 3 is the generator point here. Once we have the private key and the public key, now we are moving with the step of signing actual signature. How the signature is done? Simple. We are going to simply multiply with this message. Here is the number is 5 with the private key, which only the signer knows. So the value is 10, and we share this output to the verifier. So we simply did a multiplication, nothing special we had done so far here. 2 multiplications. First is having a private key, and from the private key we derive the public key 6. And then the another operation that we done here is just multiply with message with the private key. That's it. So that is 10. We share this 10 with the verifier. That is what the signing operation looks like.
Right. So 10 is our signature.
Signature. That's it. Just 10 is our signature. That's it. Nothing special about it. Now, how the verifier can verify it? That's also very simple. Since everybody knows the G, the verifier can simply take the S and multiply it with the G. What does it mean? Since we already know S is nothing but ED, so we are just going to expand it here. S is nothing but ED, so we have the ED here. Then the G is multiplied here. The other side of the equation, since E is also a public information, the verifier knows this message. In the case of Bitcoin world, it's going to be the transaction message. It's a transaction hash of the transaction. So here E is the other side, and is going to just multiply with the P, which is also a public information. The public is the public information for the verifier. So it is just a different way of putting the numbers. That's it. ED into G or E into DG. That's what we are talking about. Just an associative property of a multiplication. Nothing special. We are talking here. Very basic math.
Right.
If we do this with this example, S is nothing but 10 and into 3, the G, so it is 30, and E is nothing but 5, the 6 is nothing but 2 into 3, so 6. So we just expanded 30 is equal to 30. That's it. Right. So without exposing the D, what we have done here is effectively, without exposing the D to the verifier, we just showed the verifier that I know the D. Because if I didn't know the D, in this case, here are the 2. Here, if I didn't know the D, these 2 will be missing, right? If I let's say that I don't know the D, so I assume the D as 8, then the equation will fail. So that is a basic idea behind this. We are not exposing the D here, we are just hiding the D from the verifiers.
Right, yeah. So like just to hash it over there, so a verifier knows the public point G, he knows the signature that I have given him, he knows my public key, that is P, and he knows the E. So what he goes doing is like he takes the signature, multiplies with the public point and gets a number. Then he takes the message, multiplies with my public key and gets a number. And if these two numbers are same, then he says like, yeah, the guy with the private key corresponding to this particular public key is the only guy who can create that right value of S. Because if I was guessing the private key, see, like I didn't know that the private key is 2, so I guessed like 5, and so I give 5 as the private key, so my public key will become like so my public key is still becoming 6, right? Because that's public information, but I don't know the private key behind that public key, so I'm just guessing From 6, I cannot derive that the private key is 2 because D equals to P by G is not allowed in ECC. So I am just guessing. So if I guess any number other than 2, then this equation will not satisfy. S times G will be equal to E times P because my S will be something else, which was supposed to be 5 times 2, but because I'm guessing any random number, it will be something like 5 times 5. So I will give an S of 25, and verifier will say like, meh, nah, that doesn't match up with the public key and the message and the global point. So you are not the guy with the information of the private key for that public key. Does that make sense? It's a bit convoluted.
Sure. I think another question for you. So this the public key. If we go to Block Explorer, Bitcoin Explorer, and then the public key is part of that along with the signature, so that the verifier can verify that. Or is it,
Yes.
I mean, how do we communicate that?
So in a block explorer, you can always find the public key. Maybe like we can just try it out here. Any transaction will show you the public key information inside any block explorer. So that's how, like, you get the transaction data, you find the public key inside it, you find the signature inside it, you find the message. The message is the previous transaction and the transaction that is being constructed here. So all this message you combine together, you do the math, and then anybody can independently verify that the public key and the signature and the message is valid. And that's what all the Bitcoin nodes are validating for every transaction. If a transaction failed that verification, that will not be like shared across the network, right? So the network will reject that transaction. So that is always happening for all the transactions. Does that make sense?
Yeah, it does make sense. So in case of multi-sig, we have to provide multiple public keys, right?
Yes.
Okay, right. Okay,
Yes. Yes.
Thank you.
We have to, there will be like multiple public keys inside the transaction.
Okay, thank you.
Okay. Any other questions in this year? If we get this part, the next slide will be significantly easier. Here at our only we will see the equations and just similar equations. That's it.
Not this is clear to me, but I had a question as to, is there any specific term by which SG is known, as in signature multiplied by generator point? Okay, all right. Raj has answered.
Yeah, because it's a internal math part, so you don't need to like address this segment specifically in human space. So that's why it doesn't have a name.
Got it.
Okay. Any other questions? We need to be very clear about this one to move forward with the rest of the slides. So please go ahead and ask any questions. Okay. So this is a basic dummy stupid digital signatures. Obviously it has a lot of holes. It will not work in the real world. So we need a better one. We'll look into it eventually. So, but this gives an idea about what is digital signature actually means. The private key, the public key, the message, how the signing is done, how the verification is done. Just the basic schematics of what is digital signature. That's the basic idea we are trying to get out of here. So moving to the next slide. Since we just understood a digital signature, let's try to understand the magic that we discussed here. Magically, we are going to do the key aggregation and the signature aggregation and everything else. Let's try to do that, talk about that further. So as I mentioned, the elliptic curve cryptography, or the ECC, is the one that provides the special mathematics which allows us to have a multiplication, a unique multiplication, which is not a regular multiplication, which is a different multiplication on points. So that multiplication is possible, but division is not possible. That is a basic idea, basic ground that ECC gives to us. We can talk about what are we talking about here if we have time after during the Q&A. But this is the ECC that provides the multiplication, but not allowing the division. So with this understanding, let's try to do the same thing. So as we've seen, the DG is going to be the operation to arrive the public key, and D is the private key, G is the generator point, everybody knows. So let's talk, we have a two signers here, user key and Bitgo key. So user key is called as D1, the private key of the user is called as D1, the private key of the Bitgo key is called as D2. Okay, so those are the two signers here. So G is the generator point. So this one we already seen, D into G, and for user, the P1 is the public key. For Bitgo, the P2 is the public key. We just do a addition here. As I mentioned, the ECC addition is little bit different than, well, not different, a little bit drastically different than whatever we do with the normal addition. But for the sake of simplicity, let's just assume that we are going to add two numbers here. That's it. So P1 plus P2 will give us the P, the aggregated public key. The key is now a single public key. This single public key contains both the P1 and P2. Without the P1 and P2, we cannot arrive this public key. So that is one of the basic information we need to be sure about this. So just a simple addition. That's it. That's what we are doing here. But now we just did the addition of the public keys, but now we need to see how the signature also is being added or the aggregated, how the verification is done with the ECDSA. What do I mean by ECDSA is, for those who are not familiar with this, so Bitcoin originally used ECDSA, the digital signature scheme, like the one that we just seen here. ECDSA is a proper digital signature scheme, which is very complex, very sophisticated. Let's try to do this signature verification, because the public key aggregation is very simple. It's not a big deal. But when we look into the signature aggregation and the verification of the signature, how the ECDSA can help there, we need to see that, because that is an existing digital signature system before the Taproot inside the Bitcoin. So let's try to do that over here, but there is a problem. The problem with the ECDSA is ECDSA signature signing equation and the verification equation uses nonlinear modular inverse operations within here. Here the K inverse is trouble, and they are taking X part of one of the nonce here, public nonce here. It's a weird equation, much complex, which since it doesn't have the linear property, you cannot have a simple addition of signatures and the verifications that easily. That is not possible over here. So it's much complex to do here, or impossible to do here. That's what we can say. So just refresh some basics here. So what we are talking about K here? K is nothing but, as I said, this is a dummy version of a digital signature scheme. It cannot work in the real world. A real version will require some more additional mechanics to make it more secure and reliable and robust. So one of the mechanics is, other than the private key, they also use some one-time usable secure nonce. It is also a private information, only the signer knows, nobody knows. And it is a one-time nonce. It will not be reused for a different message. So it is another public private key. You can think of a one-time private key, something like that. We call it as a secure nonce. And the same operation, whatever we done with the private key and the G, the same thing we are doing here to get the public nonce. We call it as a public nonce, the secret nonce and the public nonce. So we now have like small k and capital K. These are two nonces. That's it. And
another way of like saying nonce or like private keys, like think about it as like random numbers, just like 55, nothing else, right? So no fancy point arithmetic going over here, and you just create a random number, just like you create a random private key by doing dice or like hardware, like using the randomness of the operating system and stuff. So the same thing going on here.
Yeah. So how the message E is calculated is, usually this is the way. The transaction hash, that is what message here, and the public nonce that we just created, and the public key. We are not talking about aggregation here. We are just talking about the basic ECDSA.
Single public key.
Single public key. Yeah, single signing stuff. So the single public key and the single public nonce and the transaction hash here. So everything will be combined and appended and taken another hash. That hash is called E. That is a message that we are going to use to sign this transaction. So, but let's not try to understand this equation. Honestly, I don't know. I don't even understand this equation completely. It is simply non-linear. That is a key takeaway for our scope of the discussion. So the
By
verification.
nonlinear, you can see like the signature as a function of k is not a linear equation. It's k to the power minus 1, right? And that like it's that e plus kxd divided by k. So because it's not it's at the same time the public key, the p part is inside e, and e is divided by k, right? So you cannot just add two e's together and find out the two s's together, right? So because they are both divided by k, this makes them non-linear, so you cannot do a regular algebraic addition on top of the signature. So public key 1 creates signature 1, public key 2 creates signature 2, but if you add them together, they will create a signature, but that signature cannot be validated via the summation of the public key 1 plus public key 2. So that's the problem with ECDSA. Because this equation looks like this nasty thing, we cannot like find out a summation algorithm, a easy summation algorithm on ECDSA.
Yeah, the signature part.
Yeah, I just want to mention, like for somebody who want to scour up, there is a construction called two-party ECDSA, ECDSA 2P, which is like a signature aggregation algorithm on top of ECDSA, which is like even more complex, right? It's a lot complex, and it only works for two parties and not more than twos. So it's out there. It has been like talked about whether we want to use that in Bitcoin, but by that time, like people invented or people like started using like talking about Schnorr signature deployment. And so Schnorr signature, as we'll see in the later section, is a very simple algebraic like equation where no division, multiplication, and all the weird thing is happening. It's just addition of two things. And because additions are associative in nature, so if you have k1 plus e1 d1 and k2 plus e2 d2, then you can just add them together and you can have k1 plus k2 plus e1 plus e2 into d1 plus d2, something like that. Like maybe I'm wrong, but it will get clear as Saravanan explains.
Yeah. So the key take, I hope, yeah.
Yeah, go ahead.
This nonce number ones. Is it who's responsible for maintaining this? Is it the wallet or what? And what will happen if once? I mean, if we lose that wallet, and we need to regenerate it? Because is it related to public and private key generation part, or is it separate than that?
It's separate like that in a sense, like this is generated for every single transaction. And the signature verifier doesn't need to know about this nonce. He just need to know about the final message. And
The final message will be the public nonce and the yes value that we just derived here. The public
yeah,
nonce k and the yes both are sent to the verifier. The
right.
verifier will uses this information because if you see this equation, E is already public, we know. So yes is sent by the signer, G is public, K is sent by the signer, and S is sent by the signer again. P is the public key of the signer, so everything is public. So they get the K, C and the X value of the K and the X value of the C. If they match, it matches the value. So in short, these S and the K, the public nonce and the S are shared by the signer to the verifiers.
So if you look at any Bitcoin transaction, if you like in a block explorer like mempool.space or yogg.io, you will find the signature value. The signature value, we have been like oversimplifying it, saying the signature is S, but actually the signature value is a combination of two values, S and K, side by side together. And only S is not enough to validate the signature. So S and K together called as the signature in Bitcoin.
So signer is the responsible person for to create this random secure nonce and the capital public nonce, and he shares this capital public nonce to the verifiers. That's it, and he uses this secure nonce inside the equation. That's it. Then he will throw it away. No need for this K to be maintained by the wallets.
Yeah. Is it possible for you guys to go to mempool or maybe just show us something in practical how this thing is happening?
Okay, I'll try. Let me try to share my screen.
Thank you. If I'm taking too much time, just skip it. Then.
Yeah,
I
I'll
don't
try to
want
make it quick. Can you guys see my screen? Yeah, so let's take this block, and this block has a bunch of transaction. Let's take this transaction. So this is a transaction, and the input output, this is the input of the transaction, this is the output of the transaction. If you go into details, and you will see like this is the script pub key. Okay, so this is the witness. So this part, this number 3044021, this is the signature, and this is the pub key. Anything that starts with 02 or 03 is a pub key. So here in this transaction, this is starting with 03. And this part contains both the S and K value together inside this number. And the Bitcoin nodes knows how to parse this thing into separate structures. And what's the S? Generally, like it's equal values. I guess it's a 64 or 65 byte number, where like 32 bytes of S and 32 bytes of R, and at the end, like this one is the sig hash. We can talk about sig hashes later. So this whole thing in encodes, this is encoded in hex, is a 64 byte number. First 32 byte is the S, and the second 32 byte is the K that we have been talking about. So this is available for every transaction out there, right? So this is inside this witness, you can find the signature and the public key, and the message is implicitly like calculated from this whole transaction data. And so yeah, that's how it works.
Thank you. Thank you.
Okay.
So is anybody, we'll talk about the Schnorr signature here. I think the reason for we discussed ECDSA is just to understand that there is no linearity in the equations of the signature equations and the verification equations. Because of the lack of the linearity, it's hard to do the aggregation of the signatures and verification of the signature. What do I mean by this? We can see we have an alternative signature scheme which is called Schnorr, which is introduced to Bitcoin during the Taproot as part of the Taproot feature as one of the BIP, I think 340. So that is that is a signature scheme that we are discussed now. It's very, very simple, just addition and multiplication, nothing special. This part we already seen with our dummy signature scheme, and this is the one that we just discussed here, the same. The secure one-time nonce and the message and the private key. That's it. This is the signature. With this equation, we can create a yes, and the k is the same one, the small k into j, and the k is here. The same one, we share it with the verifiers. The verifiers can use this information, and with some equation, they can easily verify it. If you want to understand why this equation is formulated in this way, this ED part provides something called cryptographic binding, which allows the signer from signer from binding his private key with signer from avoids attacks by signer from signing without the private key. So it binds this message and the private key, and the K, adding this one-time secure nonce to this equation helps to hide the private key. Otherwise, the people who are going to verify it simply can do a division, because they know the E, they know the yes, they can get easily derive the private key, right? So to avoid that, we had a simple addition operation. Since these two are very large numbers, it's very hard to derive separate what is nonce and what is private key here. That is the reason of this equation, K plus ED. That's it. We only share yes and K, as we discussed here, the same one, to the verifiers. Now, how the verifiers verifies? The almost the same equation that we've seen already. So the other side, one side is going to multiply with the G. It means K into G plus ED into G. So KG is nothing but the capital K that he has received from the signer, and DG is nothing but the public key, the one that we already seen with our dummy signing scheme. So capital K plus E capital P is the one that if this matches, then we have a SG is equal to capital K plus E capital P. If this equation is true, then we have a valid signature. That's what we are signing and verifying.
Right. So like you can notice like all the information in the last equation except for the middle part, that D, except for the D, everything is publicly known. K is publicly known. That's part of the signature that we just saw in the witness data. P is the public key that is also available in the transaction. E is the message that is also like implicitly calculated. So what the verifier goes is like, here's my signature. G is known by everybody. He calculates the left hand side, S times G, then he calculates the right hand side, K plus E times P. If these two things matches, then he goes like, okay, that's a valid signature.
We need to be very clear about this equation to move forward. So if you have any questions around it, please go ahead. It's very important to understand this equation, or at least to memorize this equation.
I think it's much simpler than the ECDSA equation.
Yeah.
And yeah.
So that Musig Explorer, the transaction we've seen, was that ECDSA signatures, or is there any way that we can find out?
Those are ECDSA signature, and because like you won't be able to see the like it will look different for Taproot cases. We can find a Taproot transaction and see how it looks like, but it probably gonna take some time for us to find one out there. But what we just saw was ECDSA signature.
Okay, so just for clarity, Schnorr's signature, is it only for aggregation, right?
No, like it can use for single signature
Single
also.
signature as well, yeah.
So every Taproot transaction uses Schnorr signature. Every non-Taproot transaction uses ECDSA signature. So Taproot is this upgrade that like allows you to create transaction using those Merkle trees and stuffs like that. And there we don't use ECDSA anymore. We use Schnorr signature. But all the transaction that is not Taproot, that uses the previous transaction format, they use ECDSA, like the transaction we just saw.
But is it required to have that this combination? Can we use maybe the simple signature, or maybe a scripts? Sorry, simple signature with the Schnorr signatures scheme?
What do you mean by simple signatures?
Apologies for the maybe I'm not using the right wording over here, but the thing is that you said that for Tap we have to use Schnorr, but previously all we are using ECDSA.
Yeah.
So Schnorr is just a signature scheme, right? So
Schnorr is just a signature scheme. Yeah, it's a way of calculating signature.
Yeah, but Tap is a way to compose a script, right?
Taproot is a way of composing the script, and inside that script there is like a script is basically a program, and most of the time what it is doing is like calling this opcode called check signature or check multi-signature, and that's a signature verification algorithm. Now you need to specify what type of signature you are verifying for that algorithm, right? So every time inside a Taproot leaf there is a check sig or check multi-sig, it's talking about the Schnorr signature verification algorithm, not the ECDSA. And every time there is a check multisig outside of Taproot, like transaction which does not have Taproot, like previous transactions, this is talking about the ECDSA signature like verification algorithm. It's just the math of these two are different internally.
Okay. It makes sense. Okay, thank you.
Let me re-summarize this to the point that we are so far. So we just discussed about what is Taproot script path, and then what is the key path. And for the key path, we are trying to do an aggregation of the public keys and signatures to save space and fees and improve the privacy. But to do that, the already used ECDSA cannot be useful. We've seen the equation; it's very hard to do with that. So Taproot introduced the Schnorr signature scheme to do that, because ECDSA cannot be done. It cannot be done with the ECDSA. So Schnorr is introduced as part of the Taproot activation. So we try to understand what is the Taproot here, and we've seen what is the key aggregation, and we just try to understand what is a Schnorr signature, how the equation will looks like for the signing and verification. That is the so far information we cover.
A question here. So another simplification is the message can directly be used in case of Schnorr signature, but in case of ECDSA, you have to find E, which is different from message. E is some sort of hash of message with other publicly available.
That's
No.
the same thing for Schnorr also.
This is same thing for Schnorr also.
Oh, all right. I thought I was all this while I was thinking E is the message, but got it.
Yeah.
Only
It's
the S and
like-
C are the difference.
It's just added with extra data in order to like provide some binding and commitment to the message, so that nobody can change the message on the fly. It's a part of like the security properties of the signature scheme.
Yeah, it will also make it fixed length and all that.
Yeah.
Just a comment from me. Like I've been searching everywhere for a slide like this ECDSA versus Schnorr, and this is a perfect explanation. So thanks for that.
Cool.
Yeah. It's quite hard to like find get it out from the bips and all, but yeah, having a presentation like this is really helpful.
Cool.
Okay, let's move ahead.
Yeah. Okay. So any other questions? Because the questions are very important. If you don't understand this part, the rest of the things will be it will not make sense.
I guess we are good.
Okay. So moving to the next part. Now we understood what is a Schnorr signature. Let's continue with our key aggregation and the signing and the verification again, because with ECDSA we couldn't do the signature aggregation. So let's try to use the Schnorr here to do the same. So the key aggregation is again same. Just the DG, TG, the same one. Just copy pasted here. Nothing special. Oh, sorry. The same here.
So we are just public keys adding two public keys together to find another public key. So that's a property of ECC public keys. If you take two public keys, you just add it. There is a specific definition. What do you mean by the addition operation for public keys? But if you do it, the output will be just another public key.
Public key. Yeah. So internally it means this. The P1 is nothing but the DGG. We are just expanding that. There nothing special here. D1G plus D2G. That's what we're talking about here. We can also interpret in this way. D1 plus D2 into G, or we can call this as D, the aggregated private key as D. For our own understanding, we can call it as a D. So this is what we have done for the key aggregation, the public key aggregation. I hope this is already familiar to us. So now we are moving to the signing part with the use of the Schnorr signatures instead of the ECDSA. So the Schnorr signature equation is very simple, right? K plus E into D. That's it. So let's create the K1 for the signer 1, K2 for the signer 2, nothing special here. And the signer 1 creates the capital K1, the signer 2 creates the capital K2. Now both the parties, both of them are added together, similar to this, almost similar to this, P1 plus P2. The K1 and K2 is added to get the K here, like this. Like the P, we get the K. The aggregated public nonce is called as a K here, that's it. So we can expand similarly here, the small k1 G plus small k2 G equal to the same thing, exactly the whatever that we've just seen here, that's what we are seeing here, nothing special here. In short, we have done the same, whatever we done, same with secure nonces and public nonces, with the same that we done with the public keys and the private keys, nothing special here so far. So now the aggregation, as we discussed with the Schnorr, since it's a linear equation, we can simply go and do the addition. No, nothing special needs to be done over here. So the same equation, K plus ED for the signer 1. So now signer 1 is going to use his secure nonce and use his private key, and the message is common to for both the signers. So he's just going to use the same Schnorr equation, signing equation. Similarly, the signer 2 does the same with his own secure nonce and his own private key and the same message here. Okay, so this is the signer equations. And whatever let's say that the signer 1 signs here, the user signs here the Bitgo signs here. So it is a 32-byte information and this is a 32-byte information. Both these numbers, 32-byte number and 32-byte number, both these number are just added here and arrive at a new value, yes, the single 32-byte number. Just an addition of these two, that's it, nothing special here. And this S and this aggregated K will be shared to the verifiers.
Now
That's what.
this becomes like the aggregated signature. So
Hmm.
two signature from two parties are aggregated together to create a signature that looks like one single signature. But that one single signature actually contains the sum of two signatures. And that is basically the magic of Musig. And Schnorr signatures allows us to do this addition that ECDSA didn't. So now we can find this one single S and one single K that represents signature from both the parties together.
Okay. So now what the verifier can do is they can simply get this S and K, one single S and one single K, and the one single aggregated public key instead of two public keys, because these aggregated public keys and these aggregated signatures are linked, right? The equation wise this is linked. We will see how it is linked. So using this P and this S and this K, he can simply verify the signatures whether it is valid or not. We'll see the verification now.
As if like it was a single signature.
Signature, yeah.
As if like is a signature created by the aggregated P on top of the message with a capital K. Right?
Yeah.
Yeah.
If you have any questions here, please go ahead and ask. So this will be used in the next slide to understand further.
Yeah, one question. Why is it not E1 and E2?
Message is same for both the
Message is
parties.
same.
If
Okay.
both of them are signing the same
transaction.
data.
Yeah.
On the same public key and on this on the public key P and on the constant K. Is it?
No, like everybody has their own individual constant K1 and public key P1, and
Yeah.
they were like producing S1 and S2. Only thing common between them is the message. Nothing else is common. Like their private keys are different, their public keys are different, their nonces are different, right?
If the public keys are different and the nonces are different, then E1 will be different than E2, right? Because E1 is not equal to message 1. E1 is...
Oh, like that's where like some extra nuances goes on. Like there is some combinations where you end up creating the same message, and that's part of Musig.
Okay. So because of those nuances, E1 turns out to be equal to E2.
Yes, like while like doing the signature communication, they will like share around their public keys, and just like the E, if you go back to the E equation, that was like HPK a message. Instead of one single P, you will have two P's inside that thing.
Okay.
I mean aggregated public key.
Right, the aggregated public key.
And the aggregated public nonce and the message is just nothing but the transaction hash. Everything is hashed here and the is same.
Okay.
The key thing is, key takeaway is, instead of one public key, one secure nonce, public nonce, we are using the two things and just doing the additions. One party is doing with one secure nonce and one public key. Another party is doing one secure nonce and another public key. Both are just added here, and one single public nonce and one single one single signature, one single public key. Everything is added. Just an addition of two operations. Everybody, one signer uses his own information, another signer uses his own information, but only for the purpose of the E, both of them using this aggregated public key and aggregated secure nonce. That's it.
Which is nothing but the addition of their each part of their public keys and secure nonces.
Got it. I'll read about how does that communication happen, but I'm clear for now.
Yeah.
Okay. Good.
So on the use case side, I think this will drag a little bit. So on, I think Raj, on your project CoinSwap, is it ECDSA 2P or is it Schnorr?
No, it's ECDSA with like regular multisig. Like the very first multisig we saw in the first part of the slide, the P2SH one. It uses that basically. It's a 2 of 2 multisig over there. But if you have pointed right, it can use a Musig implication over there. Like it doesn't have to be a 2 of 2 check multisig. It can be a Musig single sig verification, which is actually more better than privacy than using P2WSH.
Okay, thank you.
Okay, if we are clear about this part, we can move to the verification. The signing is just nothing but the two signatures are just added. That's it. The two public nonces are just added and shared to the verifiers. That's it.
Sure. Just one more question for him. What is the real use case of signature aggregation? Is it more on the privacy side? Is it on the cost side, or is something else that we're missing here?
Both. We discussed here, right? If we use a single signature instead of two signatures, like we do here, right? We use two signatures here. The verifiers will need to see the two signatures out of these three out of these three public keys. So it takes two signature informations. In this case, we will only present single signature because it is aggregated, and one single public key which is aggregated. So we says that block space, I mean the transaction size is reduced, as well as the information is hidden. We don't need to expose that both public keys are part of this script. Only single public key with the verifiers will not even know that there is only 2 or 3 or 100 or 1000. I mean, in fact, it can be theoretically it is almost any number can be aggregated here.
Yeah. So you don't expose like individual public keys in that way. By looking at that single public key, you never know whether it's one guy or 100 guy together creating that signature.
Okay.
Make sense?
Makes sense.
Okay.
Yeah. I have to read it again. Please do share once.
Yeah, we'll share these slides, and there are like lots of like reading materials also in our GitHub repo. So those are also like good to go through. It's a lot to take into head if you are like looking at it for the first time.
Yeah.
But yeah, gets easier.
My apologies, I didn't give the proper disclaimer that it requires some prerequisite understanding about some of the basics already. Otherwise, it will be very heavy content to consume for the first time.
Yeah, I guess that's generally true for everything Bitcoin. Yeah. So, okay, let's move ahead.
Yeah, okay. So we have done with the key aggregation and the signing. We are done with this. Now we need to see how the verification is done. So the information is coming from the signer, the S and K, which is nothing but in S1 plus S2. We've seen that, which is nothing but these two things. So how the verification will look like? Almost same, nothing so special here. So multiply G with this side, yes, then what will happen? This is the equation, right? This is the one that we've seen here. This is what S1 plus S2 here. So we are just multiplying with the G. We are just expanding this equation. How would this equation will look like? So we can simply take this K1 and K2 out and multiply with the G plus the the ED1 and ED2 out, and there we can, since E is common, take the E out, D1 and D2 as a plus operation and into G. So I'm just rephrasing this equation. That's it. Nothing so special here, if you understand. So again, I'm repeating. So just multiply S with G. Internally means we are multiplying G with this one, this equation. So if we spread this properly, we can take the K1 and K2 and multiply with the G, plus we can take the E from here and E from here, and the D1 plus D2 into G. So that's what this equation will look like in this stage. So let's further simplify this. Let's call this K1, K2 as K, and let's call this D1 and D2 as D.
So this is like the aggregated nonce private key and the aggregated private key. And multiplied by that G, you get the aggregated nonce and aggregated P. So what we are basically looking here is not exactly verification, it's the proof that Schnorr verification works.
Yeah.
So like the verifier will actually not do these steps inside. These steps basically says like the last line is true, which is not the case for ECDSA. So the verifier will go, here's my aggregated S, I know the G, S times G is this number. Here's my aggregated K, here's my aggregated P, I know the E, K plus E times P is this number. Is these two are equal, then the verifying is satisfied. So the verifier will basically perform the last step. And the previous steps are basically proof that why the last step is true. And the proof is basically very simple, like algebraic reorientation, right? You break down the terms into their each individual components, and because they are all like algebraic sum of each other, you just reorient them, combine them together, and you find out like everything works out at the end, just like a single signature for the aggregated signature also.
So the verifier, as Araj mentioned, the verifier will simply do this operation. He will multiply S with G and the other side K plus E into P. That's it. Because he knows the aggregated public key and aggregated K provided by the verifiers. That's it. So the nodes, Bitcoin nodes only uses this information to verify the signature. They don't care about this derivation because this is what internally it is derived.
Right. So Yashraj is asking, writing E D1 plus D2 into G is misleading. Can you elaborate?
Are you guys able to hear
Yes,
me?
we can hear you.
Oh, so I just thought that instead of showing it like that, if you just like split it up, keep it like that, and then D1 into G is P1, and D2 into G is
Yeah,
P2.
same thing. Yeah.
Because that's the communication happening, right? P1 and P2 are like exchanged internally, and they calculate
Like
things and they provide that.
it's about like how
that's
you
not
were
how-
like going to prove this particular equation. It actually not like related to the communication, how it is happening, because like the P1 or P2 are never communicated to the verifier. The verifier only knows the sum of them, the P only, not the P1 and P2. So the whole equation on top is basically proving that the construction works.
Right. Okay. Yeah. Yeah. But like internally, they are like exchanging that P1 and
not
P2.
even
They
not
like
even internally, like there is no P1 and P2 from the perspective of the verifier. From the perspective of the verifier only knows P.
He only sees this
Right.
aggregated public key. That's it. He
So
knows the public key, single
you,
public key.
so this user plus
Yeah.
Bitgo comes together and create one single
Yeah.
public key, and the verifier only knows
Yes.
that. And the point
Yeah.
of this equation is like to prove that the sum of the signature is true for the sum of the public keys also. So what it is saying in words is like, if you have two public keys P1 and P2, with that you create two signature S1 and S2. Then by the Schnorr construction, if you just add the signature number together, that is a valid signature for the same message with the public key that you will get by adding the public keys together. So as if the two
Yes.
public keys was added together, worked as a single public key, signed the same message, created a single signature, and that will be same as some of the two individual signatures.
Okay. Right.
That's
And
all
so
this
this
saying.
P1 and P2, like so, like there is like nobody, like none of the parties either are doing this P1 and P2 addition. Is that what you're saying?
No,
So-
somebody is doing the P1 and P2
Somebody's
addition.
doing
The signers will do the addition part.
Right,
Both the signers
right,
will do
right.
the P1 and P2 and they create the P. Yeah, the signers. I mean, the person who creates this. Sorry, I was wrong. Actually, it's not the signers. Actually, it's the script creators. In this case, the person who has done this created the script, right? It's a script actually.
Yeah.
This script, the person who created the script, the wallet that created the script, he does this P1 and P2 plus P2.
Right. And the K1 and K2 is done by the
Signers. Signers, yeah, right. Yeah,
by the signers, right?
Yeah, signers.
Yeah. Okay.
Right. That's a good question. Okay. So we are almost done with the music thing with additional few informations. Any other questions around here?
Yeah, like that was like pretty elaborate. So far we have concluded like this is like the heart of Musig, and heart of Musig is like coming from the Schnorr construction, and it's saying like you can do this aggregation trick and the sum of the signature remains as a valid signature for the same message for the sum of the public keys of the signers, and which is like a very interesting property of Schnorr signatures.
Why is it called Musig? Just curious.
Kind of like abbreviation from multisig, because multisig was already taken, so they called it a newer version of multisig, Musig.
Okay. If no other questions, we can go ahead. So I'm moving forward. So we just seen the key aggregation, signature aggregation, signing and signature aggregation, and the verifying of the signature. We've just seen these three. So far, we haven't seen the music exactly, but how we can do aggregation of signatures and public keys and verification operations using the Schnorr scheme. But this naive approach, the aggregation of signatures and verification, has some issues. Even the public keys has some issues. So those issues are addressed by a protocol called Musig. That's where the Musig comes. So it introduce some extra steps which solves some of the security vulnerabilities of this naive approach. We'll discuss about that. So let's discuss about this naive approaches. One of the security vulnerability is this, which is called the key cancellation attack, which is nothing but the same. Let's revise our public key aggregation, P1 and P2, the same thing, same equation. Let's say the P1 is the honest person here, P2 is the attacker here, he wants to forge something. So what P2 can do here, he creates a public key, the original public key of his own, and gets the P1 from the first signer and minus it, simple minus operation, and get the new P2 dash. Okay, and gives this P2 dash as P2 to the first signer or the script creator. In this case, the script creator. Okay, so now the equation will look like this if we expand this: P1 plus P2 minus P1, because that's what he did here. So internally, P is nothing but ultimately it will become like a P2. So if there is a single, the second signer, the attacker can simply use uses the D2 to make this transaction as a valid one.
Right. So he just basically like tricks the first guy. Instead of like honestly giving his P2, he gives a P2 minus P1. But the first guy doesn't know what P2 is, so he believes that P2 dash is P2, and he goes ahead and creates the aggregation. Now the aggregated key is basically P2. Right. And because it is P2, then it can be like solved by D2. And
Yeah.
D2 is known by the one guy only.
So in this real example, if Bitgo wants to forge the user, if you have done this key cancellation attack using the Bitgo's private key, they can spend this whole Bitcoin, whatever the Bitcoin that is sitting inside this script. So that is a original issue. Instead of the demanding signature from the user, also they can simply sign with the private key of the Bitgo and present it. The transaction will become a valid one if they have done this key cancellation attack. That is the real consequences of this attack.
So could this be why like the original Bitcoin core uses ECDSA for object multisig to prevent this attack?
No, not really, because this can be prevented.
Prevented, yeah.
Yeah,
That's what we're trying to do. Yeah.
So like in music, there's multiple rounds, right? But if you want to do it in one round, I guess we can only do multisig with ECDSA, right?
Yeah, like in multisig and ECDSA, you don't need any round with each other. You just individually present the public keys. There is no like the mathematics of multisig happening actually in ECDSA check multisig. It's like single sig validation with single sig public keys. And the check multisig will take one signature, validate with one public key. If okay, take the next signature, validate with next public key, and go on like that. So it's a series of single signature validation. And there is like no such like aggregation or like this kind of mathematics is happening in ECDSA. But why Bitcoin uses ECDSA and not Schnorr, that's a very interesting story, and it has an interesting historical context. We can get on that later.
I think the summary is there was some IP reason for which Satoshi could not have chosen Schnorr.
Basically the guy called Schnorr was an asshole. So he created this Schnorr signature scheme and he patented it, and because of his patent it wasn't developed for a long time, so it wasn't part of any big open libraries, so it wasn't like like battle tested. There was no battle tested implementation of Schnorr, so it was just sitting there rotting in his patent for like what 25 years, and and the patent actually got over just in 2008, so when Satoshi released the code. But he couldn't use Schnorr at that time because there was no like fully proven implementation of Schnorr signatures out there. And then after like the patent is over, then people started implementing it, and then by 7-8 years there is like a full on like a fully fledged implementation out there. Then Bitcoin moved into that. But we could have had Schnorr from 2008 if Schnorr was a nice guy.
Okay, that makes more sense.
Okay, you just understood the key cancellation attack with the naive public key aggregation. So Musig is trying to mitigate this issue with some additional steps and all. So what does it do? So now we are getting into the Musig. So the Musig is actually doing some extra steps on top of the naive approach, especially during the public key aggregation and during the signature aggregation primarily. So let's come here and here. What is the extra step?
So I was thinking like instead of going for the rest of the details, we are already at 1.5 hour mark. So one thing we can do, we'll probably not be able to like finish it today for the rest of the details because it's gonna go quite deep, right? So we can do another session, maybe next week or next to next week, and continue from there. What do you say?
I'm okay with it. Yeah.
Okay, cool. So for like next 10 minutes, we can open it up for a general Q&A and conversation. Otherwise, we are gonna go ahead for a whole night and will not be able to get into the Q&As. So yeah, let's look ahead and like ask some questions if you have. And so I have like one question to start with is like, so Bitgo wallet already have the Musig2 implementation done, right? And so it's already out there, and so people are already using Musig2 with Taproot.
Yes, right. Yeah. Some of the few customers, we enable it with some extra flags. It is not very public to everyone. So if the customer comes, they wants to add this flag, they can request that big team, the people will support team. They will enable this flag and they can use the Musig2 enabled wallets.
Okay, and do you have like any numbers on how much per average of a transaction is people are saving by using Musig2 in fees?
How much per hour?
Per average transaction.
Okay, okay. It's almost like 104 V bytes before the Musig2, because the most efficient one that Bitgo was using was the native SegWit 2 of 3 multisig, which was around 104.5 V bytes. Now with the Musig2, it is almost reduced to 57.5 something. So almost like 55% of reduction in the size.
Okay,
that is a big improvement.
That's a big improvement, right?
Yeah. Especially given the Bitgo is one of the, is one of the top Bitcoin transaction creator. It controls around 20% of the Bitcoin volumes, total Bitcoin volumes in the Bitcoin world. So it's a big improvement eventually once everybody adopts Musig2. That will be big saving for others. Yeah.
Right, makes sense. And do you have like, you guys have that like the library, the Musig2 implementation as public library out there in open source?
Yeah. Just to give some, refresh our eyes from the basic equations. So this is the library code. So the library code is very, very simple. The original implementation, the reference implementation written in the Python code, which is around only 500 and something reference line. So the whole Musig2 protocol is implemented here in this JS, which is around just 1,000 lines. So
it's just one single Musig.js.
Yes, that's it. No, nothing special here.
Nice.
So Musig, one of the very big advantages of Musig2 particularly, the Musig has different versions, Musig1 and Musig-DN and Musig2. The original Musig1 that was released by 2018 was having some security issues. That's where this, additional steps that we were going to see was started introduced, but it became a 3-step protocol. Instead of two, it will become a three-step protocol. Signing requires three steps, three exchanges, three different kind of exchanges. So that was the problem with the Music one. The Music DN mitigated that, but it improved it using, it improved the complexity of the algorithm significantly because it used the ZK zero knowledge proofs internally, because Music DN is nothing but music deterministic nonce. The nonce is derived deterministically instead of the random one
Okay.
for the particular private key and public key and other metadata for that transaction. But that introduced the further complexity because it required zero knowledge proofs to ensure that every nonces are deterministically derived. I mean, one signer needs to verify the other signers have really derived properly. That required some kind of zero knowledge operations. So that increased the complexity of the protocol. So then they moved to Music 2, which only a two-step, two-round protocol. One is nonce exchange, the other one is signature exchange. That's it. So Bitdev uses the Music 2. It's a very simple one. Almost, the reference implementation is 500 plus lines. This JS implementation is around 1,000 lines. Actually, most of the thousands are just,
Comments.
Comments.
Right. Looks very simple to me. And like, is there like any other wallet libraries or any system that you know out there that is wanting to use this library in their production or like in their implementation for Musig?
I don't know. I'm not. I don't know actually. Is anybody interested or not?
Okay. Okay. Cool. Yeah. Sounds really good. At some point, like I'll definitely use this at my project, but I'll have to make a Rust implementation of the same thing. But I can use this definitely as a reference implementation, and that will make the job much easier.
Yeah. So while during development of this library, the Music 2, one interesting part is during the Music 2 protocol development by the real researchers, like three people were working on the Music 2 protocol BIPs. That team interacted with one of the team member from our company. The team member from our company's name is Brandon. He wrote this JS implementation. With this understanding, he contributed some additional improvement for the protocol itself, for the Music 2 protocol itself, by introducing some further flexibility for the wallet creators. So the flexibility is something like for the Music 2, the constraint is this. You have to use a random nonce. You cannot use a deterministic nonce like we use with the single sig operations that we do for any single sig Schnorr or single sig ECDSA. For this Music 2, we need to definitely use a random nonce. But that introduces some further complications about keeping these random nonces securely.
Right.
So Brandon suggested some ways to have the last signer as a deterministic nonce and the signer. So the last signer need not to use a random nonce, and he can use a deterministic nonce. So which helps reduce the complexity of the systems in certain wallet implementations.
Right. Okay. Makes sense. So that's also like part of this implementation already.
Yes. Yeah. We have something like deterministic sign and deterministic nonce, stuff like that. Yeah.
Okay.
It's an optional one.
Really cool.
One suggestion for you guys, if possible, for the next presentation, is it possible for you guys to maybe give us some practical use cases of Music 2? The reason I'm asking is multi-sig is actually used in multiple platforms. For example, hashtag logs, DLCs, coin swaps, and there's so many. How we can we use it over there or not?
Yeah, like the practical example for Musig, been like the shortest way to say is like everywhere you are using a multisig, that's an use case for Musig. And why do you want to use that? Because it's going to like reduce the data that you are using for multisig. And if you're using like multi-party multisig, say 3 or 5 or something like that, there the reduction will be even further, even more, right? So So all those protocols, DLCs, coin swap, even Lightning transactions, right? Lightning transaction is a multi-party transaction and uses multisig. That can also use Musig.
Okay. So is it possible for you guys, once you're done with the math, maybe there's a functional use case down there discussing something over there from the consultancy side? Maybe if we have clients or maybe something we need to educate to someone.
Mm,
What new ideas? That's fine. I'm just looking for you.
yeah, okay, like I'm not exactly sure like I got your question.
So,
You
so the thing is, it's more a math here, but
mm-hmm.
the business side, if we need to sell the site to someone, a lot of patterns there, right? So in Bitcoin, so they're
Mm-hmm.
using multi-sig there, right? So,
Right, yeah.
so, so it's always from the business side. It's always about if there's new technology coming in, then we have to sell it.
Yeah, so like the business side from the idea is will be like the argument from there will be like you want to reduce your cost of operation, whatever use your multisig operation is. And I think like all the guys who are out there using multisig for whatever operations they are doing, they understand it. Like Musig has been around for quite some time, and after the Taproot upgrade, it's already there. It's just like there hasn't been libraries like this that is off the shelf that you can just directly plug in into your software and start using. So the industry was basically waiting for a deployable, a battle tested, and a production grade Musig implementation out there. And so Bitgo went ahead and created that. So anybody who is like using multisig for their operations, they can like directly use their cost like at least 50% for those operations using this library into their stack.
All right. Does Bitcoin Core support this or no?
Yeah. So Musig2 is completely off-chain protocol. It's not an on-chain protocol like we usually done with the traditional multisigs like here. Like it's on-chain. This information is presented in the on-chain. The verifier will see this information. But when it comes to Musig2, this whole aggregation operation is completely hidden from the verifiers. I mean, the nodes will not see that this even happened. From the nodes perspective or the verifiers perspective, this is a simple single signature and single public key. That's it. But behind the screens, in the off-chain during the signing, everything that we just discussed has happened during the signing by the signers off-chain without letting know the world.
Yeah, so another way of saying that is like Musig is an application layer thing. It's not a Bitcoin protocol layer thing.
Yeah.
So it's something that the wallet application will do among themselves, and the Bitcoin core node knows how to like validate like Schnorr signature. So it will basically see one single Schnorr signature and one single pub key, and it doesn't care whether 100 guys or 2 guys or 5 guys created it. So it's the application layer thing who are going to do this interaction of aggregation.
So sorry, I meant Bitcoin Core CLI, the wallet. Does
Mhm.
it support this or
No,
that
Bitcoin CLI does not support Musig2. Like this kind of aggregation mechanism is not supported by the Bitcoin core wallet yet. So Yashraj had like raised his hand yet. Go ahead.
Yeah, so I think Saravanan just kind of addressed it, I think, but I want to just like get make sure that it is addressed. Like so, Musig2 is like a n of n. It's not a t of n, and so then, but we like mentioned that we are like able to do 2 of 3 or 3 of 5, and
Yes,
it
yes,
looks
yes.
like that is like achieved through
You're right. You're
That's
right
a good
about that.
question. That's
Yeah.
a good question. Yeah.
Musig2 is just n of n or m of m. Every public keys needs to be there. Every signatures needs to be there for this particular script. It is not a threshold multi-signature like Frost or a traditional multi-signature that we've just seen. So every keys needs to be there. Every signatures of the keys needs to be there. That is a key here. For if in this case we have both the keys right aggregated here, so we need to present both the signatures aggregated and presented here. But to mitigate this limitation in the Bitgo context, we still need the 2 of 3, right? So Bitgo decided to use this as a happy path. I mean the main flow with Bitgo and the user public Bitgo and user aggregated key, and other 2 combinations in the script path that we've discussed in the beginning. So in this way, Bitgo has achieved 2 of 3 using the with the Taproot. One part is one condition as a key path spending using the Musig2 protocol. The other 2 paths, the rare paths, using the script path traditional ways. So this is how Bitgo achieves the 2 of 3.
Yeah, right. And so does this mean that in case the happy path is not being used, then the rest of the public keys are published on the chain and the fees is higher, and the privacy implication and so on and so forth, all of that happens if the happy path is not used?
Okay, so let's say that let's see that with an example. Let's say that this path is being spent here. Okay, not the happy path. This path. This is Bitgo key and the backup key, right? So in this case, we can successfully hide the user key because user and Bitgo key is added here. So user key will not be exposed to the world, and we submit this script, right? Because the user is, I mean, the signers are going to present signature for Bitgo and backup. So this script and those 2 scripts signatures will be presented to the nodes along with this hash of this script and this aggregated key. Everything will be presented to the verifiers, I mean the nodes. So the nodes will only see this script and this hash and this aggregated key. So successfully it hides the presence of the user key from the world. That is the advantage. But as you said, this will increase the cost of, because this path information needs to be presented to the verifiers, so it has to be it should be sitting on the node, I mean on chain. So that involves a cost.
Right. So yeah. So I did not know that earlier, and so I just realized when you were talking about this, and so in this case, if the happy path is not being used, then basically, so we are in that case. So basically, only the magic of Taproot is being used.
Yeah, right. Yeah, that's how we
There
achieved
is no Musig2 involvement. Right.
Yeah, right. Yeah.
And so right. So yeah, so this is very useful, guys.
Yeah.
Thank you. Thanks for this.
Welcome.
Yep, that was like a very productive and amazing discussion. And thank you guys for all the questions. Any more question?
Just one question on the resources. So I had gone through Taz Reza's MIT lecture, and it sort of helped me get some basics of Schnorr and Musig2. But are there other simple to understand video lectures or content that you would recommend? If you can include that in the notes, that's also good. But if you can recommend that right now, that's also good.
To understand the Schnorr?
To understand Musig2 in more detail.
Okay, I think other than the video that I mean that exists in the Git that Raj has shared, I haven't seen any more useful videos. That is one of the limitations we have. The knowledge around the Musig2 is very limited in the internet for now. There are few articles I will try to dig and share with Raj, and he will share.
Yeah, sure. We'll keep on updating on the GitHub repo, and that repo is there as a study material for anybody to dig deeper onto music. And on that note of threshold signature, there are things like Frost, and there is another one I forgot about its name. But those are the threshold signature scheme where you can do K of M, and those are more complex than this. But there you have to really dig into those papers and all.
The reason why we decided to go with this low level math level discussion is because since Musig2 is very new, the BIP was introduced during when we were developing very close to the completion. Few months back only the BIP 327 got approved. The BIP 327, this BIP. So till few months back, it was only in the revision stage and all. since it is very new, it is very hard to find the implementations, and reference implementation will not be sufficient. You will not find more examples and the educational content in the internet. So whoever wants to make use of the Musig2, they need to deal with the low level stuff, because they need to deal with implementing some low level stuff. Otherwise, because it's very early stage. Like in the case of, like, let's take Raj as an example. He is looking into some Musig2 options for one of his projects in around the coin join. So where he is trying to do it in the Rust programming language, right? But there is no implementation for the Rust programming language for the Musig2. He needs to understand this basic maths, the basic functionalities, the intuitions behind it, to implement the protocol itself in the first place, to use it in his project as a library or whatever it is. So that's why this kind of discussion is kind of required in this stage. That's why we thought that this discussion will be useful for some of the people.
Yes, definitely. And like maybe like this video will be like one of those useful documentations and resources that people can refer to for understanding this thing. Because as we already discussed, it is very useful for various kind of application. Anywhere you are using multi-signatures, this will become as a de facto mechanism of like saving the cost. So probably, I guess, like 10 years down the line, we'll not be using like the traditional multi-signature at all, but only using Musig or Frost or things like that. Okay. If no more further question, then we will call it a day, and we'll carry on the same discussion. We'll provide the schedule shortly, so stay tuned in our Discord and in our Twitter, and we'll finish this whole discussion and put it out in as a recorded format in YouTube, so that people can use it as educational purposes. So thank you everybody for joining in. Thank you for all the questions, and thank you Saravanan Mani for your time and such an amazing presentation and explanation. And we will catch you guys later.